For part 3, we're going to mostly talk about our prototypes, how they were designed, how they were printed, their evolution, what changed between each prototype, and what we improved upon, what went wrong, what we thought we could improve upon, and what ended up not working, what ended up working, everything in between. Our first prototype was done by early September. It was just a crappy little 3D print made with white PLA in the computer lab. Its sole purpose was to be the prototype to see if all the mechanical elements of it moved. Technically speaking, it wasn't even a stress cutter. It was just a cutter. It only had 2 blades and had teeth. At this point in the design, we still thought that we were going to be using metal, so we didn't give any consideration to thickness or how the PLA would be structurally, really. We just wanted to make sure that it was able to move. So it was very flimsy, the mechanics were very rough, and it was just a bit of a mess. This was by far the most theoretical of our prototypes. It was simply made to try and do one thing, which was move, and make sure that the parts that we were going to print on a metal printer, either the laser cutter or the water jet, were able to move. That was the only purpose of this prototype. Should we have, looking back, tried to design it a little better and try to put more effort into it? Yes. It would have worked if we had been able to print it on a 3D printer or using metal. However, there still would have been design flaws, like the teeth and the blade design being simply not a stress cutter at all, that would have really put us back. So our second prototype was made with the resin printer. Now, as we discussed before, in theory, it would have been a lot stronger and a lot more solid and flexible, and resin, again, is just generally a pretty good static material. We also made a design where we could replace the teeth very easily. That was something that we would use on later designs as well. And we made it so that the blades easily converge at a single point. Now, while all this sounds really good in theory, in practice, resin didn't work at all from the jump. The resin supports were extremely difficult to remove and ended up leaving these bumps along all of the surfaces where there was a support that you had to grind or file off. And it ended up making this really rough, tough exterior and interior that didn't even allow for proper movement. The resin itself was simply too heavy. It barely supported its own weight. The material was just too heavy, and a lot of the parts were too thin to support their own weight, so they just kind of ended up snapping and breaking. It didn't even make it off of the assembly line, pretty much. By the time that we tried to grind off certain parts and tried at least working with the material a little bit, it had broken several times, and the prototype didn't even end up making it into our hands. It didn't make it out of the computer lab or the 3D printer lab. And on top of that, we realized that a lot of the teeth connectors, when we tried to assemble it, were too small, and that the resin had actually shrunk when we made it, which just made it so that we couldn't even assemble the final product. Just to top it all off, it wasn't even a stress cutter, by technicality. It still used teeth, which, as we said earlier, have put all the forces at points, but not uniformly. And on top of that, it was still 4 blades controlled by 2 scissor pinchers that pinched them in. So it wasn't the best design, and it still didn't exactly meet our requirements for a truly uniform stress cutter. So while building our third prototype, we really made sure that we wanted to get this one right. We built it with 3D printing in mind and nothing else. We wanted the blades to converge at the center with no overlapping. We wanted to try and reduce the amount of contact that the machine made with itself, so minimize the amount of moving parts within the machine, try to make sure that everything is smooth. And we wanted this prototype to be made with PLA. It was designed with PLA in mind. It was a little bulkier, a little thicker. We didn't want it to feel flimsy, even though it was made with the flimsiest material available, basically. So by now, we already knew what worked, what we wanted to do. We knew that the teeth and the moving parts should be simple, and because they're so small, we could even print it separately. We wanted the blades to converge at a single point, all at the same time, so that it is still a uniform stress cutter, even though it still used teeth. We knew that we wanted to make it with PLA, so we made it really sturdy and thick, and we minimized the amount of moving parts besides the ones that needed to move. So we made sure that everything was kind of fit together nicely and worked. It worked really well. It works really well. It's by far our best design that's made, and it's very functional. It fits in your hand nicely. It's able to go anywhere on the egg. It fills all of those basic things that we originally wanted it to fill, and some of the new requirements that we've come up with. So the only thing that's really left is our next prototype, which is still in the works. It'll be probably one of the most complicated prototypes, if not the most complicated prototype, just because it includes some extra stuff that I haven't talked about. So, as I've stated quite a lot, teeth don't make a universal stress cutter. So, that kind of begs the question, how do we turn this into a stress cutter? How do we make sure that this project that we've spent 2 months now working on straight, how do we turn this into what it needs to be? And with our fourth prototype, we're hoping to answer that. We want to replace the teeth with blades to reduce stress points and create a truly uniform cut. And we're also working on a rotating track mechanism that will twist the blades, providing a clean, even cut with minimal force. Now, this is more reminiscent of some of the cigar cutter designs that we've seen before, but it will be a uniform stress cutter, and it will actually fulfill the role that we need it to. And I think that's about it. I want to thank you guys for listening to this and walking through all this work with me. It's been a pretty wild ride since the beginning of the school year. We've worked on this really hard. We've worked really hard on this project, and I'm glad to see it actually come to fruition. It's cool. It's a very simple project, but at the end of the day, it's something that I've worked on really hard, and I think I can say that for the rest of the group as well. We've really worked hard on this. It's been fun. It's been difficult. There were a lot of problems along the way. I remember the first iteration just felt like so far from what we really wanted to do. And watching as both the water jet and the laser printer broke, and us having to completely shift our ideas and designs to something different, it sucked, but we got through it, and I think that's pretty impressive. I'd like to thank everyone for working with us, especially the Cutter labs, all the lab technicians and lab helpers around. They've made our lives so much easier, especially pointing out things like which cuts will and won't work and recommending what we do, helping steer us despite our protests. It's been great, and I just want to say thank you, and thank you for listening.